Okay, so now for really something completely different. So we are looking at maximum independent set. So let's remind you what the problem is. We have a graph and we have weights on the vertices, and we are looking for the independent set in this graph that have maximum weight. And this is a natural problem that appears all over the place, from register allocation to resource allocation to similar problem where you want to avoid conflict, but you want to find maximum number of objects to handle in one round. Okay, so in this case, I think we already discussed this graph, right? So this is an independent set of side 3. It has weight 17, but the claim B and D, this is better because this is so heavy. So this is 25. And the claim is that this is optimal. And that's believable, right? Because D gives us 20, and then we can take B. If we choose any other thing, if we don't choose D, then we benefit that we can take E, that is 2, but then, we are down to either choosing this one and this one, and in either case, it's a worse solution. So B and D is indeed the maximum weight solution. And this example is nice because it shows you that the maximum weight and the maximum cardinality are not necessarily the same solution. So the weighted version is in some sense harder. But and to remind you, the problem in graph, finding the maximum weight independent set in graphs is an NP hard problem. So we believe that there is no polynomial time algorithm for this problem. In fact, we believe something much stronger. We believe that there is no algorithm faster than something like 2 to the O of n, right? Where the n is now vertices. You really need exponential time, right, in n. So it's kind of curious that the problem is really difficult on graph, but on trees it's much easier. And by much easier, I mean much, much easier. So let's see how to do it on trees, right? We want to find the maximum weight independent set in tree. We can take the tree and root it in an arbitrary node. So, this is the root of the tree. The nice thing about rooting trees is that now we can speak about levels, right? We have an order between a node, its children and grandchildren and so on. So it's convenient for describing the algorithm. And now we are going to look on the recursive structure of the problem. Okay. So the basic idea is that we have a tree, right? And we already looked on this problem of maximum independent set in a graph, right? And our basic idea when we look on the maximum independent set in a graph was that we considered two options, right? Either we took the node to be the independent set, right? So we said, yes, this, and of course in the tree we're going to start from the root because it's a natural thing to do. So either we take it to the independent set, but then we had to give up on its neighbors, right? So we recursed on the graph minus V minus its neighbors, right? This is V. That was one option. The other option was to decide not to take this into the independent set. And then we recurse on G minus V, right? Because, right. Now, the important thing, of course, is that when we remove V from a tree, what we remain is a collection of trees. We remain with a forest. And we can solve now the problem recursively on each one of the trees, right? Now, we have to be careful, right? Because it's not obvious how to do it in the correct way, because it's true that I can solve the problem recursively for this tree, but what about this the root of the subtree? Can I take it to the solution? So it depends whether we are, whether we are in the, what happened with our parent that is not in the problem, right? But the nice thing is that if we do repeat the same trick we did before for removing either the children or, keeping the children or removing the children, then the problem becomes easier, right? Because here, really, when we decided to take the node into the independent set and we removed the neighbor, the children, what we remained with were grandchildren, right? And every grandchildren have its own tree. In each one of those subtrees, we can solve the problem recursively and independently. And in each one of those subtrees, the root of the subtree is allowed to be the independent set, right? From the same reasoning that the previous recursive algorithm worked for the graph case. Similarly, if we decided not to take the root, then the two subtrees, or whatever the number of children is, each one of the children, we can solve the problem recursively, and the node can be in the independent set because the root is not in the independent set, right? So really what's happening here is that either recursively, we either compute the independent set of each one of the grandchildren, and we add one because we took the root, or alternatively, we computed recursively each one of the children and we took the common solution. And that's it, right? So we get right now. So the recursive problem here is going to be, we have a tree, right? And we have a node, and the recursive subproblem is for a node to compute the solution in the subtree rooted at this node. So since there are linear number of nodes, the number of recursive problem is going to be linear. And maybe let's see an example, right? So let's start with the root. We decided to take the root. We get 10, this is good. And then we delete the two children. Now we need to solve the problem for the grandchildren. So we can take C. This is the optimal solution for that. For this subtree, the optimal solution is, of course, taking I and H. So this is 9. And for E, we just take it. So this is 4, 9, 9. So this is 22. Right? And now we take this one. This is 3. And we solve the problem here. And it's 11. So this is 14. So 22, 14, and 10, we get a solution which is, so let me maybe write it in the strong characters. Oops. Right, so this is the optimal solution, and I might have miscomputed the number, so let's do it again. We have 10, we have 13, right? I don't know how I got to the, okay. So 10, 13, right? The other three, we have 3, and we have 11. Well, this is 14. That's how we got 14 there. And together, this is 30 plus 7, so this is 37, right? So this solution that is drawn is 37. Okay, now let's consider the solution where we decide not to take the root. So we have to solve the problem recursively here. Well, solving recursively here, we can either take the root of the subtree. If we decide to take the root of the subtree, then all we can do is take those two. So this is 9 plus 5. 9 plus 5 is 14. Right, this is one option. That option, we decide not to take it. And then we solve the problem recursively into those children. And this we already did, right? So it's 21, right? We take this one, we take this one, and we take this one, right? So 20, why I said 21? I don't know. I'm bad with math. And we also get this one, right? So 6 plus 7, 13, 22. So this gives us 22. And that's pretty good. Let's see what we get from the other three. So we do this. So either we take this, but then we take this. So this is 16. The alternative solution is not to take this, and then we take this and this, which gives us 14, which is worse, right? So we decided to take this and this, which is 16. Okay. So we have 22 and 16. So we get that this is the optimal solution. 22 plus 16 is 38, which is better than the previous one. So this is it. Okay, I hope you got my calculation. If not, can just do it by hand. It's a bit tedious. It's exactly why we want computers to run algorithms and not people, because it's not exactly interesting. Okay, now the recursive statement is very simple, right? You take the node U, we will want to compute T of U, the tree rotated at T. We want to compute opt of U, which is the optimal maximum independent set. And now opt of U, we have two options. Either we don't take U to the independent set, and then we just have to go over every child and ask for the optimum value. Alternatively, we take U to the independent set, and then we have to solve the problem recursively to each grandchild. Right, so this is the recurrence. Now you need to compute it bottom up. This is pretty easy because we can just order the node by post ordering. Post order traversal of the tree gives you the node in bottom up order. So we can compute the values in this order. You get immediately this recurrence, you get this algorithm. You compute the post ordering of the vertices of the tree, and then you just fill the table one by one using this recurrence, which we've seen before. And then you just return the value stored in the root. And, the root must be the last node in this ordering. The spacing is linear because we have a table of size n. The running time, so naively, it's quadratic, right? Because we have a linear number of nodes. And the summation here and summation here can have n elements. So together, this is a quadratic, n times n, right? But in fact, one can be a bit more clever because you look on the node and you ask when is charge the work involved in computing the summation to reading this value, right? So the question is how many times a value is being read? Well, a value of stored in a tree is either read by its parent, so that's once, or it's read by its grandparent, so that's twice, and that's it, right? So the number of values being read from the table throughout the execution is O of n, which implies that overall the running time of this dynamic program is O of n. Right, so that's kind of cool, and all we had to do was to improve the analysis because the running time was linear before. Okay, so here's an example. I guess I can do it despite my high standards. So let's do it, right? So HI, let me write them down here. HI D C E A R. So I'm just computing, not R. I'm computing a post ordering of this tree, right? J, G, F, B, R, right? So this is just an ordering of the node of the tree in post ordering. And now I go one by one. H, the best solution is 2. I, the best solution is 7. Okay. D, the best solution, well, we have the two options, right? Either take itself, but then we don't get anything, so this is 4. Or we call recursively on the two children, which is the better option, so we get 9. Okay, let me change color. Maybe it would improve clarity. Okay, C, well, the optimal solution is 4, right? Take the node it is itself. E, it's 9. Okay, A is going to be interesting. So it's either it's 5 and the optimal solution in its grandchildren, so 5 plus 2 plus 7, right? 5 plus 2 plus 7 is 14. The other option is that right. The other option is that we don't take it, and then we have to take the optimal of C, D, and E. C, D, and E, it's 9, 4, 9, which is of course better, so this is 22. As we say, oopsie. 22. Okay. Okay, J is 8. G is 11. Right. F is 3. B is the interesting case. Again, either we take it and its grandchildren, so this is 16, or we don't take it, but then we take the optimum of F and G, which is 14 also. Sorry, it's 14, but 16 is better, so we take 16. Okay, and now, ta-da, we reach the root. So the root either takes the optimal solution, does not take the root itself, and then we take A and B. A and B, the value one is A, and the other one is, one is 22, the other one is 16, so this is 38, right? The alternative solution, we do take B, right? So we take, so it's 10 plus C, D, E. C, D, E is 22. So that's good. Okay. C, D, E. All right. This is the optimal cost. And then we have to take the optimal of F and G. F is 3, G is 3, so it's 11 plus 3. Okay, so this seems to be the optimal solution, which is 32, 43, 46, if I added the numbers correctly, which I think I did. Okay, so the optimal solution is 46. Let's draw it. 10, right? We took this, we took this, we took this. Here we took this, and we took this, this, and this. Right? This is indeed the optimal solution. And I think what happened in the previous case, I forgot to add the 10. So that was get 36 instead of 46, but this is not a big deal. Okay, so this is how this algorithm works in this case. As you can see, it's again, it's tedious, but at least I got the right result this time, I think. Or I hope so. Okay, this is it.